All right, so thanks for coming to my talk, everybody. I'm really excited to do this. It's a little bit different than normally, like the normal talks that I would do. And we're going to do a bunch of live coding. So hopefully the live coding gods are with us today, because I don't have any video backups or anything. So we're gonna see how this goes. But just a little bit about myself, in case you don't know me. I'm an American living in the Netherlands. I'm a software engineer at Lunatech, as she mentions, and I focus a lot on Scala tooling. So most of the stuff that you will see me working on is that. A lot of things I've worked on in the past is like Metals, BSP. I'm a big NeoVim fan, so I've worked on NeoVim Metals. I've heard some other speakers at the conference mention Emacs and how it's the best editor, but I think I may have differing opinions on that. But so yes, I've worked on a lot of these different tools and like kind of specialize in where they all converge. I've had a tooling podcast / called Tooling Talks, and I enjoy a bunch of other stuff on my free time as well. But today we're going to talk about generative arts. And what is generative art? So generative art is a form of artistic expression that involves using algorithms, computer programs, or systems to simply create artwork. That's maybe like a very wordy definition, but it's just art that's generated with your computer, you could say. Uh-oh, do we have some flickering going on? It's often characterized by use of rules, but then also some randomness, but it's just an automated process to generate visual or audio-visual content. And I feel like a lot of people, when they hear generative art, they think of AI, because AI is becoming so much more popular. But the examples we'll show today are not AI. It'll kind of maybe like unveil the magic behind the curtain a little bit and show you that there's actually like some logic, like some simplified logic that you can see behind generative art and how you can somewhat easily actually do it. And we'll use one specific process to do this. So here's some examples in case you have no idea what I'm talking about when I say generative art. And these are all generated manually, none of them with AI, and they all show a little bit different type of generative art. So here's a piece called Days Fade by Tyler Hobbs. I would say remember this name because I'll come back to it, and the whole example that we'll show today will actually be related to him. Here's a piece called Untitled by Jack Rusher. I don't know if people know who Jack Rusher is or not, but I'm a really, really big fan of the work that he does. He's really big in the Clojure community and then also just a lot of other creative coding type environments. He's really brilliant. He's done a lot of really great talks in the past, and he always like blows my mind with the stuff that he generates. Here's a piece called Undulations by somebody that goes by WestGen Art, and this is also one that is not just static, it's dynamic as well and does some cool things like this. And here is another entitled one by somebody called John Chuff. And just by these few examples, you can already see that like they differ quite a bit from one another, and they're like, I could show you 20 more and they could all differ just as much from these as they do from each other. So like it's pretty broad when you hear the term generative art. But how do you do this? That's like the big question you have. And especially for myself, when I got into this, I had like, you see these cool things and you're like, oh, I want to do this. I want to generate this stuff. But then you just have like zero clue how to do it. And there's not a ton of guides that are like, how do you get started with generative art? It's either just like, here's some information on what you should use, and then here's these giant pieces and like nothing in between. So some of the common ways that you'll see this done is, the most popular one is something called processing. It's actually what we'll use today, but we won't use processing in the processing environment like normal people would do, because this is a Scala conference. So of course I had to make it more difficult and use it from Scala, but I'll explain how that's done. There's also P5.js for those of you that are familiar with JavaScript, which is actually like a JavaScript implementation of processing. One that's actually written in Scala is called Doodle. I have no idea if Noel is here, but he is the author of this and he uses this for teaching, but it can also be used for a ton of other things. Cinder is one in the C++ ecosystem. Then literally any tool that you can use to just like generate graphics or sound or stuff can be used for generative art. Like this is in no way an exhaustive list whatsoever. Why do you do this? It's fun. So like that's the simple answer. Especially recently when I started working for the Scala Center. Like I work for Lunatech, but Lunatech graciously like extended me out to the Scala Center to work on tooling. And then once I started working on tooling like full time all day, then also working on tooling at night sometime, felt like there was like no divide between my work and personal life. So yeah, I kind of wanted to do something else and explore something else, and this is what I was really interested in. So that's fine. It's just fun. So I told you to remember the name Tyler Hobbs, and Tyler Hobbs wrote this like fantastic article and also has like a really interesting blog where he goes over like he sort of pulls the cover back on a lot of the artwork that he's done. And he's like a very famous, well-known artist. He just did like a giant piece in Tokyo that like covered an entire wall in the city, like a huge building. So he's definitely like a well-known artist in that field. And he wrote this article on flow fields, and I found it super interesting because it was one of the first articles that I read that somebody sort of step by step went through like how a generative piece was made. And throughout this piece, he used pseudocode to illustrate the examples that he was doing. And what first came to mind was, I want to try to do this with Scala if I can. So I literally did just that. And what you'll see today is me interpreting his article as pseudocode, but in Scala. The process to get started with processing was a little bit complicated because processing is typically self-contained in like a processing environment where you download processing and you get like an editor that you can edit processing. You can run your code in it. Like it's all self-contained, very easy. But under the hood, it's actually written in Java. So right away when I saw that, I thought, I want to be able to use this with Scala. So the first thing I did, I went to Maven Central. I wanted to grab the processing jars, and you realize the only ones that were there were really old ones. So then I went to the GitHub repository to see like where are the new ones published. And the maintainer was like, I do not publish these jars. I don't want anybody to publish these jars because then everybody comes and they ask me questions and I don't maintain it. So please stop like publishing these jars. So all the new versions of processing aren't published, which made it challenging to get started with processing with Scala. So then I had to like download processing, unpack the application, find where the jars were located, and then take those jars and include them with scala-cli as like with using directives to just use those jars. And I'll show you what that looks like. But all that to say, the whole reason is that there is a Gitter template which does this all for you. So if you're interested in trying out processing with Scala, don't do that process yourself. Just use the template and it will load it all for you. And all the examples I'll show today will be included in this GitHub repo, an intro to flow fields in Scala. And that's what this QR code will show you. Okay. So that's it. Like we're gonna code the rest of the time. So enough of this. Let's get started. And again, we'll see how this goes because it'll all be code from here. So this is a very, very minimal Scala CLI project, and we're going to do all of our work in one file, and we're going to run everything from within the editor. I'm using Metals with NeoVim here, and it will kind of go to show like how easy it is to iterate on this, because a lot of generative programming, you do lots of iterations, you have to generate a bunch of things, you want to look at it as you're changing it. So this provides like a pretty good workflow for me anyways. And you'll notice here we have this lib, and inside of here we literally have two jars, which are the processing jars that I mentioned before, which seems really simple, but it was like a giant pain to actually find these jars in this application. So that's what those are. And apart from that, we just have a main.scala. And it's pretty simple. Inside of this main.scala, we have a main def called example, and it uses this built-in processing PA applet main, and you just give it the name of the main class you want to run, and that's it. You have settings and you have a draw method, and that's really all you need. You actually don't even need the settings. You can just use this draw one if you want. Then you could run the code, and you get this tiny little box. And you can see here, like I can like draw in it and whatever, and like that's it. But that's way too small, so that's why I have the settings here, and that's why it draws a 400 by 400 box, which is a little bit bigger, and it tracks your mouse, and that's how these things get drawn. So at the very, very basics, like to get started with processing in Scala, like this is all you need. There's not really that much to it, or it looks pretty simple at this point, all right? So let's get started. The first question you might be asking yourself, is similar to probably the question that I asked myself, is like, well, how do you get started with like generative art? Like how do you think of this thing? Like what do you even do? And one of the not most common, but like a very common way that people will get started with a generative program is something called flow fields. Has anybody heard of flow fields before? Maybe? Show of hands? 2 people? Okay. So yeah, like it's a fairly common thing that is used in generative art and other things. Like once I did this, I started to notice flow fields like everywhere. Like I would look at screensavers and I'd be like, hey, that's a flow field behind there. I bet it's the algorithm and that's how that was working. So like it's used pretty often, but the idea of a flow field is actually pretty simple. It's just the idea that you have a giant grid, and inside of this giant grid, you have coordinates, and each coordinate in that grid stores an angle. And then you basically trace those angles, and that's it. Like the idea of a flow field is simply like very simplified down to that. So that's the technique that we're going to use today. We're going to use flow fields to learn how to make some generative art, okay? And we're going to do a little bit of, we're going to create some utility methods really before we get started with anything. But I'm not going to go through them too much just because they're not that important to understand the rest of it. But we will kind of go over it. So I have like some of these methods that I'm going to pop in here, I'm going to explain a little bit, are only in here for illustrative purposes because at the end of it, I'll actually delete them and you'll see why I had them. But this method, just draw arrow, does exactly that. It's a method that draws an arrow. You can kind of ignore most of the details in here. Maybe one specific thing that you might be curious about is this push matrix, pop matrix thing. And what this is the concept of something called a matrix stack, because if you are working with a grid and you think about having to draw an angle on every point in the grid, it gets a little bit challenging to remember what the coordinates of each spot in the grid are, but then also the coordinates of like each point in your arrow and each point in the grid. That's a lot of coordinates. So what's a little bit easier is if you know how to just draw one arrow, like you know the coordinates of the arrow, it's easier to just move your grid around and draw that same arrow in the same place and move the grid instead. Then you don't have to keep track of the coordinates of your actual arrow. So this push matrix, pop matrix is just that. It's a matrix stack that moves the whole board around so then I could just draw one arrow in one place and move everything else around. But again, that's kind of an implementation detail, so I would say like ignore it for now. So for draw arrow, we're going to do just that, and we're going to just minimize it, and we're going to forget about it, okay? Then from there, we're going to grab a couple other things and we're going to walk through what they do. And this is, again, just going to give you a very basic program. So we're going to copy that and paste this here. Okay, so we have our canvas. And instead of doing 400 by 400, we're going to do a little bit larger, 1,000 by 1,000. And before I move on, can everybody see this, by the way? I want to just make sure that people can see this okay. Okay, perfect. I have thumbs up from the back. So we have a 1,000 by 1,000 canvas, but you don't really want to only work with that 1,000 by 1,000 canvas, right? Because if you do, you have like sort of abrupt endings at the end of that canvas all the time, which looks kind of odd. So you want to actually work with a little bit bigger canvas than what your screen actually shows. So that's what we're doing here. This left X, right X, top Y is where we're creating a slightly larger canvas to work with than 1,000 by 1,000. The next thing we sort of need to figure out is like, how many rows and columns in this grid do we actually want? Like, what is the resolution of this thing? And that's what we're creating here. We're just taking the width, timesing it by 0.01, and we're grabbing the resolution. And then the way we actually get the number of columns and the number of rows is by taking these coordinates and dividing it by the resolution, and then we're going to create a grid. And again, this is exactly what we talked about how the very core part of a flow field is a 2D graph, a grid. So like this is what we're creating here, okay? Then down here in draw, we are doing a couple things, but I see I have an error, so I need to make an import real quick. So import Scala Scala math, pi, and then we should be good. Okay. So we set the background color to white because by default it's gray, which is a little bit hard to see. And then all we're going to do is iterate over the columns and the rows. We're going to grab the coordinates by taking what column and row we're at and timesing it back by the resolution. And we're just going to create an angle. And for now, we're just going to take the same angle for every single coordinate, and we're going to draw an arrow given those coordinates, okay? So if I would run this now, you get a giant field of a whole bunch of arrows. That might be kind of hard to see, but they're like little tiny arrows, 1,000 by 1,000 all across the screen. And again, all this is doing is helping us visualize this grid that we have, okay? And I talked a little bit about the resolution, and just to like illustrate what this does, and I will try to do this throughout the entire talk of like, once you start getting used to doing this and start playing around with things, you realize that every little value has like a pretty large impact on the way your generation looks. Because even the resolution here, I do it like the width times 0.0.1. If I do 0.1 instead, and I save this, caps lock. Oh, hate caps lock. Oh no. Okay, we're good. Don't worry. All right. I run it again. Okay, now we got giant arrows, right? So like you can kind of tell the difference between resolution, right? Like this is really easy to like see because you have very few rows and columns, but you can imagine that as we start to generate stuff, like this isn't going to work well because like you need way more rows and columns than this. But it just goes to show you that like the resolution makes a pretty large difference, all right? But this is boring, right? Like all of the angles are just the same. Like that's not really what we want. We want them to curve, right? And the way that we can do that is to cheat, not necessarily cheat, but instead of just doing the same angle, the easiest thing that we can do is instead of just doing pi times 0.25, we can sort of like look at the row that we're in and the total amount of rows and times that by pi instead, and we can at least get like a normal curvature. So what we can do is we could do the row to double, and we can times that by the number of rows to double, and then we're going to times that whole thing by pi. Okay? So just this small change, if I run this now you see we have this, we're introducing this curvature, right? You can kind of see that, yeah, it starts pointing right and curves down. And again, this is only 1,000 by 1,000, but if this was like 10,000 by 10,000, you would see that it would just continue to curve. And eventually, if it was large enough, it would just make one big circle, basically, okay? But again, with flow fields, like we have this curvature, but we need to somehow like follow that curvature to actually do anything. So we need to refactor this a little bit because we created this grid up above that you can see here, but we're not doing anything with it because we're just like iterating over stuff and drawing on the screen right away. So let's refactor this a little bit and let's actually store some of this stuff, okay? So I'm going to copy this 4 here, and instead of drawing this arrow here, what we're going to do is we're going to actually do, we're going to take the grid that we created, and we're going to, for the column and the row, we're going to assign it to row to double, and we're going to divide that by the total number of rows to double, and again, times that by pi. Struggling a little bit because right before this talk, I was like, oh, I can't have a dark theme, and I always use a dark theme. So I switched it to a light theme, but now I can't see where my cursor is on the screen on my computer. So I'm just like, I think I'm in the right place. I'm just going to start typing and hope that's the case. So anyways, we're storing this now instead of drawing it. So then over here where we actually grab the angle, instead of like taking the angle that we created before, what we can do is we can access it from within the grid. So we can say, hey, this grid, this row, save this, run it. It should do the same thing as we did before. So like no change, right? We just refactored a little bit to store it, and then we have to reiterate over it again, okay? So now let's grab another helper method, okay? Because we want to visualize the line that we're actually drawing. So we're gonna have a helper method that is going to draw a point. So let's jump down below this draw arrow, and we're going to put another method called draw point. Again, totally not, that's not what I wanted. Okay, I was nervous. Do you guys see what happened right there? Okay. Brace the syntax, it's awesome. But anyways, so we have this method. If you didn't see what happened, nothing, just ignore it. So we have this draw point method that all it does is just draw a point at a single place, not a big deal, right? And what we want to do now is introduce some more values to help us generate this. So if I go back to where we were before, so here's the draw method. We iterate over, we store them, we draw the arrows, and then right after we draw these arrows, there's nothing in my register, but I want something in my register. Hold on. Copy. So we're going to do a couple of different things. We need a starting point, right? Like where we want to draw this line from. So we're going to have a variable x and y, and bear with me because we're using some vars here. And we're using some vars here because underneath the hood, processing is like crazy imperative and very like mutations everywhere. So when I was doing this, I just said screw it and leaned into it. So don't be like, oh, this shouldn't be mutating all this stuff. It's fine. Don't worry about it. So we have the x and the y, which is the starting point of where we're going to start drawing our line. Then we have the step length, which is going to be how many steps do we take before we actually draw another like dot. then how many steps total do we take, okay? And we'll play around with these values a little bit just to like show you the difference that they actually make, because they make huge differences. So let's now paste in another snippet here. And what we're going to do is that for all of the steps that we have, we're going to grab the offset, because remember, if we have these steps, but we have a grid of 1,000 by 1,000, but our grid is really a little bit larger than that. So we always kind of need to do this mapping back and forth between like what point in the grid we're actually at, because again, the grid is a little bit larger than where we're at. So we need like the offsets basically. We also want to do some checks to make sure that like the point that we are getting is not actually off the visual like grid. So because we don't want to plot those, so we can just ignore them. And we need a couple more imports, it looks like. So let's do this, and we're going to take costs, and we're going to do sign, and then we're going to jump back here, and this should be fine. Okay, so all we're going to do is we're going to take the points that we start at rather, and we're going to draw them, and then we are going to grab the next step based off of a little bit of math that you see right here, just using cost and sign to grab the previous angle, then assign that to the x and y, and we're going to iterate over the amount of times we have. Make sense, kind of? Okay, everybody's tracking. So if I draw this now, you'll see that we do plot along the actual curvature that we see. And at this point, like I think the resolution doesn't make a ton of sense. So like let's go back to where we were in the beginning and do this by 0.01, run this again. And now we have a whole bunch, and now it makes a little bit more sense to actually see how these are done, right? But I mentioned the like step lengths and the steps, they make quite a bit of difference. So let's take a look at those. So if I change this step length from 10 to say 30, it just means that there's a bigger length between each point that's drawn. You see now that they're more spaced apart, right? So like to kind of make sense how the step length changes things. And the steps, if I maybe make this way less to like 30, you'll see that I actually won't go quite as far because I'm not taking as many steps, right? So pretty makes sense. Like these are all values that people are tracking, like why they make a difference and stuff. But again, this is a little bit boring, right? Because the curvature that we've created is simply based off of a little bit of math to just do a round curve. And that's not exactly what we want. Flow fields, like if you remember the picture that I showed, we're like all flowy and pretty and cool. And like this is not flowy, pretty, and cool. So one of the most common algorithms that people use for flow fields is something called Perlin noise. Has anybody heard of Perlin noise before? I see more like head shakes from Perlin noise than I did for flow fields, which is kind of funny to me because I wasn't super familiar with Perlin noise before flow fields, so it was the other way around for me. But Perlin noise is super interesting, and it's used about 90% of the time that people use flow fields because it's a really easy way to get like a smooth, continuous value across a 2D plane. And when I was first researching what it was and how it worked, I found a couple quotes that really helped me. And one of them said that Perlin noise is a way to generate controlled randomness, which I thought was a pretty interesting way to look at it because one point on the grid is sort of, it's random, but also semi-related to the point next to it, which you'll see, visualize in a little bit. And then I found another sentence that said, Perlin noise is a random sequence generator producing a more natural harmonic succession of numbers that follow a standard random function. And again, that one maybe doesn't help a lot, but those are two things that help me, and I'll show you kind of what they do. And because these things are so popular, processing actually has built-in support for Perlin noise. So you don't need to like worry about writing your own Perlin noise algorithm or anything. You can just use the one that they have. So if we look at where we assign the angle in the grid here, we can change it. And all we need to do is, I'm going to grab a little bit of code here so I don't have to type it all out, is this. So we're going to take the X and the Y. We're going to scale them a little bit. Typically, whoops, oh my gosh. Okay, good. So we're going to scale them a little bit because the values need to be between certain numbers when you pass it into the actual function. And then the way that we get the angle using Perlin noise is we call this noise function. We give it the scaled X and the scaled Y. Then we times it by 2, we times it by pi, and then we times it by 2. And again, you can play around with these values, and you will get crazy different results again. And it's sort of like you just have to play around with it and see what you like and use what you like later. So again, not much has changed here, but let's look at how this actually changed what is being generated. Okay, that one was not a good idea because it started at the point, but like the algorithm drew it off the top of the screen, so you don't really see it. So bad first example, but you deal with that. But now you see again that we have one starting going down basically, and then it curves around and goes to the left. So you see that here. But let's generate a couple more just to, again, visualize. Again, this one's going up, so you don't really see it. Let's do this. Now you see it going around. Do it again. And now you see it way in the corner. Now you see here, like I'm having some bad luck here, but like let's work with this, right? Because like if it keeps drawing off the screen, maybe let's just change the starting point, right? So if you go back to this x and the y starting coordinates, I'm starting in the middle of x, but in the top. So let's just do 500 by 500 maybe and start in the middle of the screen. And then no matter what, you'll see it. So now we again have this, generate it again, have that, generate it again, have that. So makes sense kind of how Perlin noise more or less works. And again, like at least when I was doing it, you're kind of like always changing these things around because right away it's bugging me that like my steps are too far apart and I really want like more steps. So maybe I would do 100 of these instead and generate. And okay, now this is a little bit nicer, okay? But let's actually try to make something nice out of this because realistically, I think already we have like the core basics of what we actually need to start like generating this stuff if you put it together and start iterating on it. So let's get rid of these arrows because we don't really need the arrows. I mentioned that they were just like a helper thing to help us visualize the grid. So that we can just delete this. Let's delete the whole arrow thing. So get rid of the arrows. Now I'm going to have an error up here because I don't need to draw the arrows anymore. So I can get rid of all this code as well. And let's regenerate. Go. Okay. So now you can see it without arrows. Same, it's working the same exact way. We just don't have the visual representation of the arrows anymore. Let's do it one more time. Okay, pretty similar to the first one. And another one, again, pretty similar to the first one. And now we have a little bit different one. All right. So the next stage that we probably need to do is let's draw multiple of these things instead of just having one. One's boring. So we need to do this. Then now we have to do a little bit of refactoring again, right? Because you notice this 4 here, it steps through all the steps and just draws it once, but we want to do this a whole bunch of times so we can kind of get rid of this. And let's refactor this into a function called, we'll call it draw curve, and it will basically do exactly this, but in a function, so a method rather. So let's copy this. We'll go all the way down here and paste this right underneath this. And again, you'll notice that it's pretty much literally the code that we just did up there. So we can go back up and we can get rid of all of this code because we just refactored it out. So let's do this. And now what we're going to do is we're going to do one more thing. Because we don't also need this starting X and Y anymore because we're going to draw a whole bunch of lines and we obviously don't want all of the lines to start at the same place. So let's do that. And you'll have noticed that down below, I actually like generate the X and Y's. It's passed into the function. But we need one more thing now. We want to know the amount of lines that we should actually generate. So let's do a line count here. And let's start with, I don't know, 10 lines or no, that's boring. Let's do 50 lines, okay? And at this point, all we need to do is iterate over the amount of line counts that we want to do and call that method. So we can do, again, 0 until line counts. And then for each of those things, each of the counts, do this. We'll just do draw curve. It's really hard to type when you have no idea where your cursor is. Steps, the count, and the step length is what we'll pass it, okay? And what's wrong? Okay, random, import Scala util random. All right, so now let's do this. Okay, whoa, like what the heck happened here now? Like, why is this going crazy on me? But realistically, you can't really tell it, but it is only that many lines. But what happened at this point is that we're iterating over something that we're introducing randomness into it. And you didn't notice it before because we didn't have any randomness that was continually going every tick. But the way that processing works, and I'll stop that in case it's crazy. Oh, I saw somebody trying to take a picture, so never mind. I'll put it back up, and then you can do it. But the way that processing is working is that there is a tick going on in the background, a bunch of ticks, and you can control how fast that tick is going or what's going on. And you don't realize the tick until you actually have something that introduces randomness like this. So yeah, it's going crazy. This is obviously not what we want. The fix for it is rather simple, actually. So what we can do is inside of our draw method at the end of it, all we have to do here is add something called no loop, which guess what? Causes it to not loop. And then you get this, okay? So again, the amount of lines that we wanted to draw are here. So we can soup this up a little bit, and let's say we want to do 500 lines instead of 50 lines. And now you see a whole bunch of lines on here. And you can do this, but they all start to blend together if you keep going up. So like, obviously don't do that. But these are still dots, right? We don't want dots. Like we want kind of lines to go through the field. So let's change that up too. So instead of doing this line method that we have, this draw line, or actually draw point rather, sorry, draw point. We don't need to do this anymore, so let's get rid of this as well because we, again, don't need it. If we go back to where this is being used, instead of calling the draw point, we want to create a line, and you can actually just say, give it the coordinates that you want to draw it. So we have the x coordinate, we have the y coordinate that we can use, we already have the next y, or the next x coordinate as well, and the next y coordinate, and we can just do this instead. And now if I run this, now you'll see in 1 second a whole bunch of lines that are created. So again, like one step closer to where we were doing. But this is also a little bit hard to visualize because like there's a whole bunch of lines, but they're all the same color. So maybe let's add some color into this as well. So if I go into this draw curve method and right down here before we actually call the line, what we can do is do this. If that counts is divisible by 2, then we give it one stroke color. If it's not, we give it another stroke color. And now if I draw this, you should see half the lines being one color and half the lines being another color, okay? And at this point, it's really faint because I'm using some colors here that probably you can't see. So let's change that as well. And what we can do is we can say the stroke weight should be, I don't know, 5 instead. Try running this again. Okay, now it's a little bigger. Maybe we want it even thicker. We'll try 10. Okay, now we have it quite a bit more thicker. And we can play with these values as much as you want because I'm not sure if you can tell, but you can actually still see the little dots that are really close to one another. And you can make these more pronounced. For example, if you would put that the step length should be larger, let's say we want the step length to be 50, and you run this again, it becomes much more visible where the points are actually between the line. Again, I can't really tell if you can tell that or not, if you can see that or not, but let's make a change to the colors to maybe help you see that. So this last value here is actually making it a little bit opaque, so we can get rid of that and just use the true colors. Run this again, and now it's much better. You actually don't see the points anymore because it's just a solid line that's being drawn here. Okay, does that make sense? So again, we didn't have to learn that many concepts or even do that many things to really like get the core concepts of how you can generate this type of stuff. And just with the simple values that we looked at, like how big is your step count? How many steps do you take? How many lines are you going to draw? What's the resolution of your thing? Changing these values can like really change the art that you're generating or whatever you're generating in crazy ways. And the more you play around with it, the more you can tweak the algorithms to do different things. So, for example, I mentioned the Perlin noise that we were using. We were taking it and timesing it by pi, and then we were timesing it by 2. Well, what happens if you do something different? Like you times it by 5 and you run it again, and then you get all sorts of crazy stuff, and things start to divert away from each other because it's like a larger difference. And again, now you notice that you saw the edge of the line a lot. So maybe you want to make the lines a little bit longer. So you go to the amount of steps, and maybe instead of 100 steps, you want to take 500 steps. Because remember, we have logic in place that if we go off the grid, we stop pointing them anyway. So it doesn't matter. We can make this 10,000 steps, and it's only going to plot as many as it has room for. So you start to really see the difference of how these work. So let's jump back into this. So this is just another example of one that I generated that I thought looked kind of cool. But again, you can go with thick lines, thin lines, transparent lines, different color lines, different algorithms, and it will generate all sorts of different stuff, okay? And if reading is more your thing, Everything that I just showed you is actually in a blog post called An Intro to Flow Fields in Scala, which I do kind of a step-by-step guide. And the code samples that I linked earlier correspond to the images in this blog post as well. So if reading is more your thing, you can check out the blog post here. And that's it. Thanks for coming.